Alrighty, hello everyone, my name is Justin Houston and this is part 2 of my exam 2 video using Google Collaboratory. So just getting into the swing of things here, we're still trying to solve for those dimensionless groups that we do not know using the Gilliland and Sherwood or Schmidt relationship. So continuing with that here, we are going to first import numpy as np. What that's going to do is because numpy is within the Python library, we're going to be bringing that in and importing it to support any coding or arrays that may be needing it without this video or throughout this video. So next we are going to be importing plotly.graph objects as geo, and what that does is we may want to graph some data here at the end of this video, so we can import a scatter plot using this through the graphed object library, and the objects library, and hence the geo for graphed objects. So next, import I forgot to hit tab or enter, not tab. So there's a here. So next, import plotly.io as PO, and this is going to be a two-step. So I'm going to type this next part out too. PO dot templates dot default. Hold on. Default equals plotly underscore dark, and what those last two lines did, so within Google Collaboratory, a default setting when creating a scatter plot is going to be a white background, and just to change that up and create like a cooler looking graph, we want to import a dark background. So that's what those last two lines were doing for us. Next, from there, plotly.subplots imports make subplots, and what's that's going to do for us is we can create some tabulated data and place those side by side into a graph if desired. So now we have that from scipy.optimize imports minimize, and what that is going to do for us, let me just run this real quick. Okay, it worked. So what that last line is going to do for us is, at first here, this next step, I'm going to be taking some randomly generated numbers and randomly distributed, but in the long run, what we want to do to help solve for those dimensionless groups is minimize like a realistic tabulated sum square error that we will be incorporating here. So now that we have that that section performed and run, ran, we want to start doing that randomly distributed, because we don't know those exact points yet for the Reynolds and Schmidt number that are to be calculated. So I would generate like a set of random numbers here, randomly distributed through a range that I'd given in my first video that those numbers are acceptable, or those dimensionless groups are acceptable. So starting with that, we want to do the Reynolds number, numpy.random uniform, and then bring in those acceptable ranges. So for Reynolds, it was 2,000 to 35,000. And then I'll explain what this, the 100 is, that's for setting in our array. We want 100 randomly generated, regroup, with 100, we want to create an array with a set of 100 data points that are randomly generated, which we can use within the Sherwood formula here, which I'll do after I do the same thing for the Schmidt number. So have that Schmidt numpy.random .uniform, and then the acceptable range is 0.6 to 2.5, and then we want that set of 100 again, and then, like I said, now we can bring that into the Sherwood formula, which was given 0.023 times the Reynolds number to the power of 0.83 times the Schmidt number raised to 0.44. And what that is, as we already defined, that's the Gilliland-Sherwood correlation with the exponents and coefficients that they had found that fitted their data correctly. So next what we want to do is add an experimental error. So we'll do the same thing, Sherwood equals numpy dot random normal, and then we want to add a location for the Sherwood number, which what that's going to do, so we will start generating those normally distributed random numbers, and that location is going to be centering those numbers around the Sherwood values. So now that we have the Sherwood, we want to add a scale, which, like I said, that's going to be adding a standard deviation around the means of those values to be about a 10% error around that Sherwood number again. So 0.10. And then, like I said, centered at the Sherwood number. So I think that's all we want. Yeah, I think that's fine. So run that, looks good. So next, kind of going off a little from the coding, I was gonna do like a separate video, but I didn't know how to like shove it into this part of the video without splitting it up. So what we know here is, and I guess I'll just type this out in just text form so it doesn't ruin anything. So we know here that there's a general form of the Sherwood value equaling A times the Reynolds to the power of that B times the Schmidt number to the power of C, which is basically this just the general form of that that Sherwood number that I had previously defined within this area. And so what we can do now is, when creating these arrays, we can form a log mean or natural log version of this by taking the natural log of each side. So in doing that, we do natural log Sherwood equal to natural log C plus A natural log times Reynolds plus B natural log of the Schmidt number. So this is, like I said, the natural log form of the exponential to create a linear regression. So in doing this, if I were to show this out in hand form, we could create a design matrix, which when multiplied together, these two design matrix, they form a linear regression of the following format, which is A equal to, and like if I were to show this out, you'd have different variables representing two different arrays. So you'd have x to the transpose of x times x, and that's in the first bracket, and that's all. And then you want the negative inverse of that. All that times the transpose of x again times y. So, and in doing this, that's basically what I would be getting to if I were to show it by handmade with these two design matrices. So now we want to do the same thing, but here in Google Colaboratory. So in doing that, okay, I just want to make sure that, okay, we're good. So in doing that, we want to say, we want to do numpy dot column underscore stack. And I'll explain this whole thing once I code it all out. It's just easier for me to do it that way. Dot ones like Sherwood comma NP log of Reynolds, and then we want that Schmidt number. So NP log of the Schmidt bracket parentheses. So what that is doing with the np.ones underscore like, that is producing an array of all ones, which would be that x value that we wanted, and it's producing the same shape within that array. And then when we bring in that column stack outside of that, the array is formed exactly as, like, pretty much what it's saying is that you have stack columns formed, and then producing the from there, within those, we want to produce the log values of the Reynolds and the Schmidt number, which we did, and then that gives us the final design matrix we want. And then we can then, what I'm going to do next is assign a value to, or a variable to what we just solved with this. So Shift Enter. As you can see, we just got that array of values that we were looking for. So what we want to do here is, like I said, assign a variable. So we can call this design matrix. Hold on, I just, sorry, I went back to one too many. Design matrix, so DM for short. Now let's assign, running that again. Okay, looks good. So next, what we want to do here, and I'll explain here in a second, we want to calculate those coefficients and exponents that we do not know. So in doing so, I don't want to define a variable yet. We'll do numpy again, dot linear algebra. Dot inverse. And this is, as I previously explained, the X transpose at dimension or design matrix. And then we want an at again, X dot transpose at, and I'll explain what these ats are here in a brief second. Dot log of the Sherwood number. So in explaining this, like I said, the x dot t is the transpose of x at x for the matrix multiplication. That's what the at sign is we're creating a multiplication of the two matrices, of the design matrix. Also, when I define that NP linear algebra dot inverse, this is performing a linear algebra inverse to to give us an inverse matrix of a 3x3 transpose. I'm trying to think what I want to do next. So when we, I guess, yeah, what I'm trying to say here, you can see with the like outside part, the couple last two design matrix multiplications, we want to do that with a transpose to get the natural log of the Sherwood number. So once we do that, Shift Enter, trying to see here. Okay, so I believe I figured out what I did wrong exactly in that previous step. As you saw, there was an error with having an undefined variable. So trying that again here, numpy.that linear algebra dot inverse, as I already explained. You want the inverse of this. Now, what I did incorrectly that previous time is using an undefined variable. I just forgot to use the design matrix variable that I defined, dot the transverse at where's the at sign, at that design matrix, and then we want to take design matrix multiplication at the design matrix variable transpose at, which is multiplication again, times the numpy log of the Sherwood. Okay, that looks good. Sherwood. So run that. And as you can see, we get that array produced of general values, which are somewhat close to what we were looking for. You can see they're off by a little bit, which is because of that 10% error that we had originally defined. So it's good to see that they are somewhat close, although yeah, they're good so far. They're just randomly produced. And what we want to do is store that in a variable of a, and then Shift Enter. So now that we have that stored, so keeping that going, what we want to do next is so I think what we want to do is we want to form like a function, I believe, to minimize creating, instead of having that that randomly generated error, we want to get a constant absolute error value. So in doing so, we can do we can define a as I said too, with that that minimize function up here with the SciPy, we wanted to minimize that sum square error eventually, so we can do that now. Sum square, we'll call it, of p, which is just a parameter that we want, so this is going to give us like a constant absolute error, I believe. And yeah, I think we can keep rolling. So from there, we want to go return mp.sum, and I'll explain this all in a second. Sherwood minus p of 0, which is going to be the first term in the set, or times the Reynolds, using the same formula again, raised to the power of the parameter of the second term, which we put is 1 because it starts with 0, which is why I started with 0 with the first part, times the Schmidt's raised to the power of p of the second term, or the third term, excuse me. See, that's why you gotta be careful with that, because even though I'm getting tripped up a little bit, And all this is raised to the power of 2, or squaring it all, I guess you could say. And then it's all divided by the Sherwood squared. So this is going to give us like a constant relative error again. What we are doing using the sum function, we are adding up the sum square error, which creates a direct nonlinear regression. And then we can then subtract. What we are doing here is we take the Sherwood data number, and we are subtracting the complete model, which I had already explained with this hashtag up here, which is just a text. So we subtract the model from the data, and then we are then treating each data point with the same amount of error, giving us a constant absolute error. So in doing that, we want to, I think we want to, yeah, we want to minimize that again. So minimize that sum square error, given those value guesses for each unknown that we were looking for, which is A, B, and C. 0.44. And so what that last step is going to do, it's going to minimize that sum square error of the given coefficients and exponents in the Sherwood equation. So we can shift enter that, and it all looks good. So next we can start getting into the plotting of this, the tabulated data. So first we want to print a comma np exponent of a first term. And what that's going to do is we are printing the normal values of that normal function that I've given, function A, while the we take like the exponential function using numpy of the 8th zero term. So now that we have that, it prints out those tabulated data again, which is pretty similar to what we had originally found in those initial guesses. So since it looks good, I think we can go and continue making our plot that we want to use to help visualize our data points. So going on, figure is equal to make sub. Obviously I forgot a space. I'm just going to restart this. Figure equal to make underscore subplots. Also want figure dot add, and I'll explain all this once again whenever I'm done typing it. Figure dot add underscore trace go scatter 3D. It's always important to make sure that that D is not capitalized, or else it's not going to run correctly since it is a function. X equals the Reynolds number, Y is the Schmidt number, and Z is the Sherwood number. Mode equals markers, comma, marker size equals 5, comma, marker color equals Sherwood. What else do I want? Oh, we can also change the opacity, I believe. Marker opacity, and we want that to be 0.9. Trying to think what else we want to define here. Oh, the line length, or width, I mean. Marker line width equals 1. And then finally, I think we can change the color of the line. So marker line color equals white. Yes, I think that's what we want. So what that's doing, we are bringing in that subplot, which we are doing using that figuring, and we can create a trace of a three-dimensional plot, like I said, with that scatter 3D of the graph objects with the geo out in front. And then we can bring in, as I first defined, the x equals Reynolds, y equals Schmidt, and z equals Sherwood. We are defining the different axes as each dimensionless group. From there, we can also incorporate the different graph traits, which I did. I used marker mode, which is including using markers as the certain plot points. We then create the size of those, the color of the markers, the opacity, and then we can also incorporate the line size and color, which I included there at the end. From there, we want to, since we have these arrays here with us, we can create two arrays for the Schmidt and Reynolds number, and then we want to undo those arrays and split those off into two variables. So what we're going to do here is doing the Schmidt grid and Reynolds grid, and here those are our two variables, and we set that equal to the numpy.mesh grid, which that mesh grid is going to be doing the unpacking of the two arrays, which are assigned to each of those variables. So in doing that, that's why we use the mesh grid. Then numpy.linspace, linspace of 0.6, those accepted ranges, 2.5. Was it 2.5? Yeah, 2.5. And then a set of 30. Then we want to do the same thing. So what we're doing is we are creating an accepted range for the Sherwood grid and the Reynolds grid, determined off of those preset values that were already given. And then we're creating a list of 30 for each of those arrays. So when this would actually print, it'd first create two sets of arrays, just split by comma, but then we can separate those. And we can then incorporate these into a variable of the Sherwood formula, which can then be placed on the grid as well. So continuing NP, we want that linspace again for the X and Y variables. For the Reynolds grid now, which is 2e to the 3 power, and then 35,000 with a set of 30 of those. And then finally, like I said, we can put that into a Sherwood grid. Set that equal to the formula that we know, 0.023 times, using that Reynolds grid we created, to the power of 0.83 times the Schmidt grid we just created. We raise that to 0.44. So yeah, that looks right, I think. Like I said, that's all incorporating into the grid. So now we want to, since we have those X and Y values for each array, we want to zip those up into a series of X and Y, which will end up taking those and like putting them into smaller groups and pairing them with each other. So in doing that, we have the for function I, comma, j, comma, k in the zip function. And then I think we do the grids next. Well, we can just go for it. Yeah, the zip objects, which is the grids, grid underscore the Schmidt number grid, then the Sherwood grid. Then we want to add a line tracing to this, and creating a color of that line with a set width as well. So in doing that, we do a fig dot add trace go that scatter 3D, and then once again, since we incorporate with the for ijk, we can then assign those to the X values that we previously defined for the different grids. So X is equal to the I, Y equals J, and Z equals K. And then we incorporate the mode, which would be a line mode. And then we want to do line equals dictation, then we want, this is where we incorporate the color of the code 0066FF, and then a width of equaling to, yeah, that's a good value. So like I said, that's zipping up those pairs. And then finally we want to do the same thing. So that's creating like what I want to say. So yeah, so one other thing to note is that what I just coded is going to be having the lines in the grid going across the page from one form to another. And what we now want to do is switch that code we just typed to get the lines to go into the page compared across to create that full grid. So what we do is we just switch the order of the Reynolds and Schmidt numbers to get that to occur. So we can just copy and paste everything that I just typed for that, and then get that in there. Like I said, the only thing you want to do is switch the Reynolds grid and the Schmidt grid. So we do Reynolds first, comma, Schmidt grid, and that's equaling that mesh grid again to once again to assign each array to the correct ones. So we want to change the set values again, 35 E3 and the 2 E3, same set of 30, but the only thing different here or there is nothing different. We're just switching the values. 0.6 and then 2.5 with 30, using the same Schmidt grid formula, and also the same for function. So lastly, since we have that, we want to just update the overall layout, so we can fix anything, including the width, and like anything that we may not want. Right now we can get rid of things like titles or legends that we may want as well. So we can just, or include titles, I mean, but get rid of like a legend or something, because what this will typically do is create a legend on the side, which is just obnoxious, that we just don't want. So getting to that, with the figure, we want to update the layout. We can do height to be 800. You usually want it like 7 to 900. Width can also do 800. You want to keep those consistent. Like I said, with the legend, it's going to be just very bold, so we just don't want that. So we'll say false to get rid of that. The scene. And then yeah, the titles we want as well. X-axis underscore title. We want that Reynolds to be called Reynolds. Then we want the Y-axis title to be equal to the Schmidt. So SC, and then finally Z-axis title equals Sherwood. So I think that's all we need. It looks good. Let's just run it real quick. So Shift Enter. Looks like I just forgot a dot with the lens space. Let's try that again. Same thing since I copy and pasted. Alright, so we got our graph here, and as you can see, we have our data points plotted, and then we have, it looks good, a sloped with curvature, with the grid forming each and both ways, which is, like I said, when we define those grids with the MP mesh grid, one's creating those lines going into the page this way, and then when we reverse the order of the Reynolds grid and the Schmidt grid, it creates the lines going the exact opposite way, which forms the grid that we are looking for. Also, we have that black background. Also, the different axis titles, Schmidt, Reynolds, and Sherwood numbers, both labeled correctly. So yeah, I think that's what we are looking for. So that answers our overall question. So